The Wheatstone Bridge. The circuit shown in figure called a Wheatstone bridge is used to determine the value of an unknown resistor X by comparison with three resistors capital M, capital N, and capital P, whose resistances can be varied. For each setting, the resistance of each resistor is precisely known. With switches S1 and S2 closed, these two switches, these resistors are varied until the current in the galvanometer G is zero. The bridge is then said to be balanced. Part A showed that under this condition the unknown resistance is given by X equals MP over N. This method permits very high precision in comparing resistors. And part B, if the galvanometer G shows zero deflection when M is 850 ohms, N is 15 ohms, and P is 33.48 ohms, what is the unknown resistance? X. Okay, so let's start with part A. I'm going to look at the currents that will flow in this circuit. So I call the current that's coming from the voltage source I epsilon, the current going through the resistor N IN, the current going through the resistor P IP, the one going through X IX, and the one going through M IM, and they add up and give me I epsilon, which is going back to the voltage source. So if I write the Kirchhoff current law at junction B, then IN is entering this junction, IM is leaving this junction, provided that there is no current in this branch, because the bridge is balanced. Then I can write the Kirchhoff current law at junction B tells me that IN must be equal to IM. It's the same current that goes through resistors capital N and capital M. The similar situation occurs when I write Kirchhoff current law at junction C. You can see that IP must be equal to IX because there is no current here. So IP is equal to IX. So this basically tells me that the two resistors, capital N and capital M, because it's the same current going through them, they are connected in series, and capital P and capital X are connected in series as well. So that's what I find out. Now, what is the equivalent resistance of N and M? The equivalent resistance of N and M connected in series is N plus M, and the equivalent resistance of P and X will be P and X connected in series, so it's P plus X. And the voltage that appears across these equivalent resistances, voltage between points A and D here, is epsilon, the battery EMF. Okay, and when I have these two equivalent resistors replacing N and M and P and X, I see the same voltage appears across them, so they are connected in parallel. So I can see that the equivalent resistance R and M and RPX are connected in parallel. The same voltage epsilon appears across them. Okay. Now, if I look at this loop, KVL1 loop here, so starting at this point, point A, and I go back to point A by following this path. So basically, I'm flowing in this direction. So this is going to be capital N times IN. So this is plus minus. That's the voltage drop here. And then there's no current on this branch. And then I have IP flowing in this direction. It is minus plus PIP. So it is minus PIP. So the Kirchhoff voltage law tells me for the first loop here, KVL1, is NIN, the resistance N times the current IN, plus 0 because there is no voltage drop here. And then here on this branch I have minus PIP. This must be equal to 0. And if I write the same Kirchhoff voltage law for this loop, so this is going to be MIM now. So I start here, MIM, and then I go here, it's going to be minus XIX. So KVL2 equation is MIM minus XIX is equal to 0. Now, let's rewrite these two equations here. NIN minus PIP is equal to 0. And then I have MIM, but IM is equal to IN. So this is going to be MIN minus XIX, but IX is equal to IP. So XIP is equal to 0. And at the same time, the current going through the resistor N is epsilon divided by the equivalent resistance N plus M. And the current going through the resistor P or X is epsilon divided by P plus X, the equivalent resistance. That's Ohm's law. So, if I look at this equation now, NIN becomes N times epsilon divided by N plus M minus P times IP, which is epsilon divided by P plus X, is equal to 0. Now you can see that these epsilons will cancel out, and I will be left with, if I write this with the common denominator here, this is going to give me NP plus NX minus NP minus MP is equal to 0. So that's NP plus NX minus NP minus MP is equal to 0. Two NPs will cancel. So I will be left with NX minus MP is equal to 0, which will tell me that the unknown resistance X can be written as MP, the product of the resistances M and P divided by the resistance N. So this was basically the suggested equation, X is equal to MP over N. So I showed that under this condition, the unknown resistance is given by MP over N. Now let's give it some values here. In part B, we have the unknown resistance X should be equal to MP over N, and the value given for the resistance M is 850 ohms. P is 33.48 ohms, so it is 850 times 33.48 divided by N. N is given as 15 ohms. 15. So that gives me X is equal to 1897 ohms. Basically, it's an application of this equation for three known resistances, and provided that the bridge is balanced, the unknown resistance is 1897 ohms. Okay, so once again in this Wheatstone bridge, the first thing I discovered was if there is no current flowing through this branch, this current IN and IM is the same. The same current flows through N and M, so they're connected in series. The same current IP and IX, they're the same, flow through P and X. So the equivalent resistance for this one is M plus M, for this one is P plus X. The voltage is epsilon, so epsilon over N plus M is this current, and epsilon over P plus X is this current flowing through these two branches. When I write Kirchhoff voltage law for this loop, it is NIN minus PIP equals 0, and for this one, it is MIM minus XIX is equal to 0. And here I note that IX is IP, and here I also note that IM is IN. So if I take either of these two equations and write down the current IN and IP as epsilon over M plus M and epsilon over P plus X, I obtain this equation. And when I substitute the numbers in part B to this equation, I can get the unknown resistance.